Hello everyone and welcome to the second video of the series Abstract Algebra. In this video we're going to give some examples of the notion of a group. So let's start by the first example that will be very familiar to the watcher, and that will be the integers under ordinary addition. Let's now prove that it's actually a group. So first of all, ordinary additions of integers is of course closed, because if we have two integers and we sum them, the result is still an integer. So we have that the operation is closed. Furthermore, the operation is associative. The operation meaning that for all integers a, b, and c, this is true. Furthermore, every element has an inverse, in particular minus a, and the identity is 0. In fact, every element, if we sum 0 to element, the result is the element itself. We also notice that we have an extra property. In particular, we know that addition of integers is commutative, meaning that if we switch the order, the result is still the same. And this is called a commutative property, and we will now take the opportunity to define a group with such a property. So we call a group G such that, actually let's also explicit the operation, such that if the operation star with respect to which it actually forms a group is commutative, is called an abelian group. So we'll remember this definition because we will encounter it quite often. So with this said, let's switch to another example, actually to a counterexample. Let's consider the natural numbers, for example, under addition. So as you can see, this algebraic structure is not a group. Well, why? Well, addition of natural numbers, which is defined by the piano axioms, as a corollary of, the axiomatic definition of the addition of natural numbers, we know that the addition of natural numbers is commutative, yes, and it's also associative. So for every a, b, c in n. However, there's a problem. In fact, suppose we have an element, we can find actually an element a in n, such that does not exist an element b in n, such that a plus b is equal to 0. And here, of course, supposing that, we take in the formulation of natural numbers in terms of the piano axioms, we consider to include 0 inside it. Sometimes the quote-unquote starting point is postulated to be 1. Let's now include 0 inside the natural numbers for this example. We can find an element such that an element for which the sum is the identity is not possible to find. In fact, we can actually take this element to be 2, and we see that for all b in n, 2 plus b is not equal to the identity 0. So this is actually an example of an algebraic structure that is not a group. Now let's give another example of an algebraic structure that is not a group. So for example, we can take the integers together with ordinary multiplication. And why is it not a group? Because again, we can actually find an element. We can take, for example, 5 in the integers, and then we note that there's no element in the integers such that 5 times a is equal to 1. So let us now give a little bit another slightly more interesting example. Let's consider the set A of the following elements: 1, minus 1, I, and minus I. Then this group under ordinary complex multiplication forms a group. Let's see why. So to explain this, actually we will also introduce the notion of a Cayley table, which is a table that is used to represent the results of multiplications of elements inside a group. So it is represented in the following way. So we place all the elements on a line and then all the elements on a column. And then we draw a table like so, where in each box we put where the box, for example this one, given by the intersection of a given row with a given column, will yield, we will place here the result row times column. So it is important to remember this this convention that we will adopt, because of course because we will often work with groups that are not abelian, so not commutative. However, even if you use a reverse convention, it's perfectly fine, and just remember to stick with that so you don't confuse yourself. So for example, to build the Cayley table for this group, we will have to take the row and multiply by the column. So this is for example, for the first row we will have row, in this case 1, so we're doing this row first, 1 times column 1, so this will be 1 times minus 1, 1 times I, 1 times minus I, minus I. We move to the second row, so again, row minus 1 times column 1, minus 1 times minus 1 is 1, minus 1 times I is minus I, minus 1 times minus I. Then I times 1, we move to this row here, I, minus 1, 1. And here again, minus I, 1, minus 1. And so this is the Cayley table for this group, which is again all the possibilities of multiplication of elements of this group. And let's notice that from this table we can actually make some considerations and deduce that this is actually a group. So let's see why. So the condition number 1 that we need is that the group needs to be associative. So we won't check the associativity because, well, it is included in the Cayley-Dickson construction of the complex numbers, which we don't need to know what that is for this moment, because of course it requires the knowledge of fields and algebras and all of this stuff. We don't need it. Let's just take it for granted. So we will just check for the existence of an inverse element. So for each row we will see if there's something that yields back 1. So for 1, yes, there is, it's itself, so 1, the inverse is 1. Then for minus 1, inverse is minus 1. So for I, its inverse is just minus I, and for minus I, its inverse is I. So yes, for each element there's an element such that if we multiply them, then the result is 1. So there is an inverse. So now what about the identity? Is there an identity? Yes, because if we multiply something by 1 and multiplication by the identity is commutative, we get the same result back. So there is also an identity. So of course the operation again is closed, and in this case it is also commutative. So this group is an abelian group. So A is an abelian group. So this is we will later see what an order of a group is. We can actually define it right now. It's really simple. An order of a group is just the cardinality. So order of a group, in this case A, is just the cardinality of the set, of the underlying set, so the number of its elements. In this case it's 4. So this is a group of finite order. And let's now actually try to give another example. There's a group of finite order which is not abelian, so it's not commutative. So let us introduce it here. So let us now consider a group Q given by 1, actually plus or minus 1, plus or minus I, plus or minus J, plus or minus K. This is called the quaternion group, and it's a group of order 8, so double the order of the last group. And the multiplication rule for this group is that plus or minus 1 times one of the units, imaginary units, we'll call it just EI, is going to be equal to plus or minus EI And then for the multiplication of the units with themselves, we will use the following graphs to guide us. This graph that will guide us. And to interpret this graph, we just use the following interpretation. So basically, if we the multiplication of two elements, so to get the result of the multiplication of two elements, we will just have to follow the arrows. So if we follow the arrows in the direction of the, so if we follow this connection in the direction of the arrows, we will pick the result with a plus. If we go against the arrows, so in the opposite direction, we will take a minus. So for example, in this case, suppose we want to multiply I with j. So we go from I to j, we follow the direction of the arrow, and following the direction of the arrow, we go here. Then here the result is plus k. So I plus I times j is k. But now suppose we want to multiply k times I. We go follow the arrows, k times I. The result is j. So now suppose we want to multiply j with I. So we go this time against the arrows. So the result is minus k. So I hope this is clear. It's really easy to understand once you get the grasp of it, but I mean, it's way simpler than other ways to define this multiplication, because there's other definitions which do not involve graphical systems, such as this one, involve Levi-Civita symbols and the Kronecker deltas, which for in this case it will be an overkill, absolutely. So this is the graph that will guide us. Let's again build a Cayley table for this group. So let's put all the elements, and I'll now fill it without going through every single. And I'll now fill just a couple. Now I'll just fill a couple of rows, and then I'll autofill all the rest. So let us first build a grid. So I won't fill. So I'll now just build a grid to make it a little bit more aesthetically pleasant. Okay, so now let's fill some of the rows. For example, let's fill this one. So I times 1, it's I times minus 1, minus I times I minus 1. Oh, I forgot to mention that all these imaginary units will follow the rule I squared is equal to j squared is equal to k squared is equal to I times j times k is equal to minus 1. So this is another important rule that they have to follow. So with this in mind, let's fill this row here. So I times 1 is I times minus 1 is minus I times I is minus 1, I times minus I is 1. I times j, we said above, it's k. And I times minus j is minus k. Then I times k, we can see it from the graph, I times k is minus j, and I times minus k is j. So actually I forgot to fill these rows here. Oh, never mind, I'll do it now. So let's do this row right here, so j, actually minus j. So let's see, minus j, then this will yield j, then minus j times I. Minus j times I will be j times I, then negated. In this case will be, we're going in the reverse direction, so here, then here, so the result will be j times I is minus 1, minus k. But minus k times minus 1 is just k. Then minus j times minus I will just be equal to j times I, but we saw that j times I is minus k, so this is minus k. Then minus j times j is just equal to j squared times minus 1, which is 1. Minus j times minus j is minus 1. Minus j times k from this graph we see is we're going to in the direction of the arrows, so we pick a plus. J times k is I. So it's minus I in this case, and then minus j times minus k is I. So now as an exercise, try to fill in the remaining rows, and in order to check if the calculations are correct, I'll just jump back in a couple of seconds to the complete graph for this group. Okay, so here it is, and let's, as before, use this table in order to explain why this is actually a group. So So for the inverse element, let's see that for each row we can find an element such that, so a column, for each row we can find an element in the columns such that the result of the multiplication is 1. For example, for 1, its inverse is 1. For minus 1, its inverse is minus 1. As you can see, for I, in this case, its inverse will be minus I. And for minus I, its inverse will be equal to I. For j, its inverse will be equal to minus j. And for minus j, it will be equal to j. And for k, it will be equal to minus k. And for minus k, its inverse will be k. So there is an inverse. Okay. Then there's an identity, and that is 1. We can check, and it's also, of course, commutative. So we can see that the row in the column 1 will just yield as a multiplication the element that was multiplied with back. So for example, here with the row 1, we'll have 1 minus 1 I minus I and so on, and the same way in this column here we will have all the elements back. So the identity is 1. And as last property, well, as we can see, all the, of course, results of the multiplication were parts of the group back, so the operation is closed. So with this said, the last property to check is actually associativity, which we won't check, and we will just quickly explain why we can say it works. And again, here we would need the rigorous definition of quaternion multiplication, and well, if someone is curious to know, well, here in order to justify why this group is associative in a quick way, not using algorithms to figure out well, the associativity or not of finite groups, there are some of them, but I will just mention the definition of quaternion multiplication that is built in a similar fashion to the one of complex numbers, so via the Cayley-Dixon construction, which technically we're falling into a kind of vicious cycle if we try to justify this rigorously, because such a definition requires already that someone who has to read it knows what a vector space, what an algebra is, and what is an algebraic structure. So let's just avoid justifying it rigorously for now, and let's just say in a hand-wavy fashion that this algebraic structure is associative, making thus it into a group. So we, as a final consideration, so how can we classify this group? This is in order 8. Is in order 8, finite. Of course, it's finite if it's order 8, but let's just specify it just for the sake of it. Non-commutative group. So this is another cool example of a group that is certainly fun to make. So now let's give a last example and then conclude this video, and then proceed with other examples in the next videos. So the following example comes from linear algebra. So if the viewer is familiar with matrices, he can skip this brief introduction of a matrix that I will give. Actually, if the viewer is not familiar with the concept of a matrix, I'll just give it briefly here and non-rigorously. You can think of a matrix as a block of elements, where in this case let's consider real matrices. So A, B, C, and D are all real numbers. So it's this block of real numbers. In this case we're considering a block of 2 rows times 2 columns. So 1, 2, 1, 2, so 2 rows and 2 columns. Let's consider this block of 2 columns. We call this a 2 by 2 matrix. So you could ask, what if I add other columns, I add other rows? Yes, you can do that. In general, we talk about A1, so A11, A12, and so on and so forth. So in this case, and then here A21, up until we could say AN1. So imagine we have here N rows and here M columns. This is a N by M matrix. So the number of rows, number of columns need not to be the same, and we can have as many rows, as many columns as we want. So this is a matrix, and we can actually add, and we'll actually also multiply, but let's consider addition of matrices for now, just addition. we can actually add matrices together. I'll consider the simplest case that we gave above of 2 by 2 matrices. So imagine we have a matrix A, B, C, D, and a matrix A prime, B prime, C prime, D prime. Then the addition of these two matrices will just be given by the matrix given by the matrix where each entry is given by the sum of the corresponding entries of the starting matrices. So in this case, A plus A prime, B plus B prime, C plus C prime, D plus D prime. So this is the definition of addition of matrices that we'll use. And now let's state this fact. In particular, we will consider the algebraic structure given by the set of 2 by 2 matrices. We will write it as such. So this just means all 2 by 2 matrices under matrix addition that we'll denote with this plus here. And we claim that this is a group, and in particular it's an abelian group. So let's see why. We will check again, associativity and commutativity follow immediately from real associativity. Well, why? Because if we have two matrices, imagine A, B, C, D, and then A prime, B prime, C prime, D prime in M2 by 2 R, well then there's some, so let's call this M2 and M1 just for shorthand notation. M1 plus M2 will be equal to this. But we know since this is a real number, this is a real number, and so on, by the commutativity of real addition, we know that this is true. And so this is equal to M2 plus M1. So in particular, addition is commutative. So we notice also that this is closed, of course, because all these entries are real, and their sum is real because real addition is closed. So it is closed. It is also associative. By the same reasoning we did with commutativity, it's a immediate corollary of associativity of real addition. And as a conclusion, we know that for each element, so for each m in this set, that we can call it A, B, C, and D, then the matrix minus A, minus B, minus C, minus D is its inverse, that we'll call minus m. So for each element we can find an inverse, particularly this matrix here. In fact, you can check that if you sum them, you get this matrix here. That is the identity. And in fact, this is for the inverse. And for the identity is the matrix 0, 0, 0, 0. Again, where 0 is the identity of real addition. And well, why? Because if you sum it to any matrix of the set, you will get the element you summed it to back. So this is a group. And more generally, you have that the following is a group. So you just have to, in all these considerations that we made above adapt like very, very simply. And the discussion we made above is almost the same. So it's really very easy to check this, considering what we said above. So with this example, we will conclude this video. In the next video, we will talk about other examples of groups, and we will also talk about the dihedral groups and symmetry and groups of symmetries, which are very interesting topic and application of group theory.